edit out that first part right there. Oops. Yeah, it is what it is. All right. Force diagram time again. Woo! So we start out with doing the force diagrams. As a reminder, we just draw the three objects. We have three objects here: box 1, box 2, ground. When I say ground, you can also picture that as just part of a giant planet, or a planet. 1, 2, and ground. And again, I am not claiming that box 1 and box 2 are hovering. I am just claiming that there's a box 1, a box 2 in the ground, and I'm just drawing them, happen to be in that order. At this point in the course, we have talked about two different forces. We have talked about normal force and weight, or generally gravitational force. Put a little W in parentheses there. 4. All right, so what do you remember about weight?
Everything had, well,
What's the requirement for there to be weight?
mass, 2 masses.
All right, that's the requirement to be gravitational force, but what is weight specifically? How is weight a subset of gravitational force?
One huge mass and one small mass.
Yes. Okay. And huge, we're talking planet or moon size, we're not talking elephant. Elephant is small on the scale. All right, and normal force. What's the requirement for there to be normal force?
Contact.
Yep. All right, so what are the forces involved here? What has weight?
Both boxes.
Okay, which way is weight acting on box 1? Now, forces come in pairs. Where's the other part of that pair?
Up from box 2.
No. What is causing this weight?
Everything.
No. What's the other object? Forces require 2 objects. Box 1 is one of the objects. Nothing? There's got to be something.
Box.
No. Sorry?
Box 2.
All right, if box 2 is it, because the second person who said box 2, if box 2 is it, that means that if I could remove box 2, box 1 would just stay hovering.
The ground.
Oh,
Yeah, the ground is causing it. It's the planet, the large object. So we have this force upwards acting on the ground. That is the pull from box 1. All right? One pair of forces down.
weight on box 2.
Okay, acting which way?
Downward.
And where's the other part of that pair?
From the ground.
On the ground. This is the one coming from the ground. So we're now talking about the one from box 2 on the ground up. And the reason why I'm picking on the preposition that you use is that if you get straight that on, I mean, that's where you're drawing the arrow. The ground pulls down on box 1, so I draw my arrow down on box 1. Now there is a problem like this, and I've seen this too many times on the complex problem that will be on the test, that has been on the test, and you will have one similar to it. What's wrong with the diagram as is, besides the fact that we haven't finished it? But why is what we have so far misleading?
Is it because we haven't distinguished which forces on the ground are acting on which boxes?
Yes. If this is true, we are claiming that box 1 and box 2 have the exact same weight. They weigh the same thing. And we cannot make that assumption without more information. So we do need to differentiate these W's somehow. And we do that with the magic of a subscript. And I like the subscript to be something that's meaningful to where the force is acting. Some people will just, there's a slew of weights in the problem, and they'll just start on the left-hand side, and there'll be 1, and then 2, and they'll just work their left to right, top to bottom. But to me, it's a little bit easier if the subscript has meaning to the object. So weight 1 is acting on object 1. Weight 2 on object 2, and this would be weight 2 down here. Give myself a little bit more space. Weight 2. All right, we know this cannot be complete because if this were complete, box 1 and box 2 would be in free fall, but they are not. So what other forces are involved in the problem?
Normal forces.
Okay, which way is the normal force acting on what object?
Between box 1 and box 2.
Okay, there's contact there, so which way is the normal force acting on box 1?
Downwards. Well, up.
It's one of those two.
Yeah.
We've eliminated left and right.
Upwards.
Is it down?
If it's down, that means we have these two forces acting down. What's holding box 1 up?
Box 2.
Box 2.
Then the force on box 1 from box 2 is up. This is the force that is on box 1. Something's got to be holding it up. And also normal force is a pushing force. Box 2 is pushing up on box 1. So put a little y there with a little subscript. Where's the other part of that pair? Okay, which way is it going on box 2?
You going down?
Yes, it's always in the opposite direction. So if y1's like that, we got a y1 coming down here. If you do not believe this force exists, then you've never had your older sibling sitting on top of you at some point in your life. You're not feeling your brother's weight, I assume brother. You're not feeling your brother's weight, you're feeling that normal force he's exerting on you. All right, and we got one more pair of forces.
Between box 2 and the ground.
Yep. Which way is it acting on box 2? So look at that y sub 2, or y sub g, either one, and then down on the ground. If you put this stuff into soft dirt so that an impression will leave behind, it's this force right here which is leaving that impression behind.
Forces.
Yeah, we'll get more. The test level problem, probably be somewhere from 20 to 40 forces on the test level problem. All right, any questions on this?
So, have we declared what a y force is normal?
Yes, I use y for normal. Let's see if it's a little better. Apparently not. That's slightly better. This way you get to see my knees. All right, so rookie mistakes. Did I do the rookie mistakes last time?
I don't think so.
All right, so rookie mistakes. Well, this rookie mistake number 1. Rookie mistake number 1, absolutely no subscripts to differentiate them. Rookie mistake number 2. Completely opposite. And so on. So W. Oh, I guess we can do subscripts this time since we're not combining mistakes. 1 and 1, 2 and 2, 1. The student is putting the force on the source and not the recipient of the force. Because remember, all forces will have a source and a receiver. And you're supposed to be putting the force on the receiver of that force. And probably the most frustrating of the rookie mistakes differentiate here, 1, 1, W2, 1, 2, 1, 1, Y2, Y2. The no man's land. I've done this a whole lot over the years. It's possible that once is too many, but I have no idea if the student knows what he or she is talking about when I see something like this. Now, sometimes I will take a guess. Sometimes I got the gap right there, and they'll have one like this, and the other one's right here, and they'll have one like that, and that's labeled Y. Let's go in the other direction so it actually matches this problem. So Y1 and Y1. Something like that, I can probably take a guess and figure, all right, they're intending this to be going up here. But in something like this, I know what the answer is supposed to be, but the student has not communicated to me that the student understands. And so I tend to ignore something like that. And, oh yeah, rookie mistake number 4. Probably should codify these at some point. You know, the force diagram we have over there, and then they'll have this Y sub G, and then that's 1, and then a Y sub G down here. They'll put a normal force between two objects not touching each other. Okay. Normal force and friction both require contact. All right, questions before we actually use this to solve a real life problem? Not one that's going to shatter your belief system, but it does apply to real life. Let's see, I want to keep that. Get the rookie mistakes. All right. That's a person standing on a scale. All right, so a person standing on a scale. So the question is, assuming that this is working, it actually is measuring weight about 20 pounds lighter than it should, no, 30 at this point, 30 pounds lighter than it should be. And assuming the scale is working, what does the scale measure?
220.
Okay, but I'm talking about why 220?
Because you're high end.
You're just gonna guess what my weight is?
Yeah.
It's a little bit less than that usually, but I haven't weighed myself properly in a while. So you're saying it's measuring my weight?
Probably measuring normal force gravity again.
All of them at once? That's a lot of forces. It's measuring one force. The question is, what is that force? Okay, my weight is what you're going for? Yeah, force of gravity is the correct answer. Weight is just more specific because it's weight because I'm being attracted, the gravitational force is between me and the planet. Gravitational force, recognize the gravitational force, there's a gravitational force between anything with masses. There's a gravitational force between me and the ceiling right now. It's tiny, fortunately, or unfortunately. It turns out it'd probably be pretty cool if I could, get that extra leap by jumping in a building. Although I probably would have hurt myself a lot growing up. All right, so the claim is by weight, so let's take a look at that. So we will do person on scale, on ground. The force diagram is the same, so we have this Y sub P for person, and W sub P. We have W sub P on the ground, and we have this Y sub P here. So then we have weight 2 here, or weight S for scale, weight scale. And then we have this normal force, Y2 up, and this Y2 down. I think that matches the force diagram we have over there. Which one of these letters represents my weight?
from where?
Pardon?
Anywhere?
The question, which one of the, I have Y sub P, W sub P, Y2, W sub S, and Y, and I think that covers them all.
Is it WP?
Yeah,
WP is my weight. I agree with that. There and there. If the scale is measuring my weight, how come that force is not acting on the scale? It can't be measuring my weight because my weight's not acting on the scale. What force am I actually exerting on the scale?
What? IP?
That is what a scale measures. Now, my weight is about 220. If I'm bouncing up and down, how's my weight changing? Is it? Is my mass changing as I bounce up and down? Is the mass of the earth changing while I'm bouncing up and down? Is the distance between me and the earth changing appreciably? Me and the center of the earth.
No.
So my weight actually is not changing at all. But the scale is going to read something different as I bounce on a scale. If you've never bounced on an analog scale, you should do it sometime. As you bounce on an analog scale, that scale is going zipping back and forth. I'm weighing anywhere from 50 pounds probably to 300 pounds just by doing this. Or scales don't actually measure weight. They measure normal force. Now, why do we claim that it measures our weight? Because if acceleration is 0, that means the change in velocity is 0, which means that actually the total force is 0. If one of these is true, the other two are true. This is known as equilibrium. So if I stand on the scale with a velocity of 0, if my velocity stays steady, my acceleration has to be 0 because my velocity is not changing. If my acceleration is 0, the total force acting on me must be 0, which means the force up on me must equal the force down. They have to balance each other out. So if I'm just staying still on it, then these two values have the same magnitude. That's why we say it measures weight. But in reality, it's measuring that. A real life application to box on ground.
You say it's measuring force, normal force?
Normal force.
Normal force.
It's normal, because that's the force I'm exerting on the scale. The gravitational force between me and the scale cannot be measured with, unless you've got $1 million equipment. Questions to hear? Come on, Daniel. It's about to get more exciting, I know. All right, time for
What is it next to the F?
next to the F. That's total. It's my attempt at the word total. You can write net also if that's easier for you. One of these and the board. Yes, any teacher can just draw up a ramp on the board, but how many of them are actually going to bring a piece of wood into a classroom? Well, you can just stop right there. How many teachers are actually bringing a piece of wood into a classroom? All right, I put the block right there. Why does it not slide down the ramp?
Friction.
So I now introduce the third force of this course, friction. I have a gap up front. basically, they're gonna have a gap there and then I'm gonna put 2 more letters in there, just if you're prepping or thinking ahead. So this is box on ramp. All right, so let's talk a little bit about friction. The symbol I use for friction is what I call the Baroque F, sort of a curled F like that. Some people will do a capital F with a lowercase f to represent force of friction. And by the way, that's also the same letter I'm going to use for frequency later on in the course. A requirement. The requirement is contact and desired relative motion. We will definitely get into more detail by what I mean by desired and relative. The direction of the friction, so I'll just make it darker here, with respect to the objects. It is parallel to the surface, parallel to surfaces of contact. Therefore, it is perpendicular to the normal force. And opposite to desired relative motion. That is the direction that friction will act. So the box wants to slide down the ramp, and so friction is acting on the box up the ramp. Relative to the ramp, the box wants to slide down. That's what I mean by relative motion. Relative to what the object's touching. And then direction of the pair of forces, since forces come in pairs. They are side by side, anti-parallel. Because gravitational forces point towards each other, normal forces point away from each other, friction forces act anti-parallel. So now, box on ramp. And for this, we'll make the ramp part of the ground. Now, when doing a force diagram of box on ramp, as we separate the objects, some people will straighten out the box, and there's not anything inherently wrong with it, but people who straighten out the box tend to have other arrows pointed in the wrong direction. So my recommendation is to draw the box, when you're drawing the object itself, draw it at the same orientation that is, and then I'll draw the ramp here. And see if I can actually get the same angle, at least closer to that angle. There's no ramp. So we now have 3 forces to consider. Let's take the easy one, the weight.
Just between the box and the ground,
Yep, which way is it acting on what?
downward on the box, upwards.
The direction of the weight, it defines actually the word down. So we have weight acting down. Now the arrow drawing up is actually from the earth itself. So you don't have to draw it on the ramp itself. You can draw it on the earth or below, somehow indicating it just somewhere around here. So I'm just gonna put it there. Gravitational force, done. Normal force.
Between the box and the ramp,
Which way is it acting on the box?
upwards.
No. Ah. Normal force. What does normal mean again?
Perpendicular.
Yes. It is perpendicular. The surfaces are that way. The normal force is acting that direction.
Upwards or relative.
So yes, perhaps I cut you off too soon after you said upward. Where's the other part of that pair, since forces come in pairs?
On the ramp.
Going which way?
Down perpendicular.
Yeah, okay. Better be the opposite direction of that. So weight and normal force are not opposite each other, as some students really want to force into every problem. And lastly, friction. If the ramp were frictionless, would the box slide?
Yes.
Which way would the box slide? Therefore, which way is friction acting on the box?
Opposite to the relative motion.
Yep. So friction is acting this way on the box and this way on the ramp. And done with our fourth force diagram problem. So slowly adding complexity. Ready for the next one?
Yes.
The rest of you, I assume your eyes are saying yes, so. This time, the ramp is not part of the ground. So we got, wedge or ramp, whatever you want to call it. So I got that separate from the ground. So now we got the situation like this. I have three objects involved. I've got my box, I've got the wedge or ramp, and then I've got the ground. Yeah, by the way, there've been a number of problems where I've had a ceiling involved on the complex problem. And so when I separated the objects, I had ceiling as a separate object, and I think some people interpreted it as just a line dividing one part of the problem to the next part of the problem as opposed to an actual object. So watch out for that. All right, so I have box and ramp. What? Somebody, new voice. Somebody who has not spoken up yet.
There would be weight pointing down, being exerted on the ramp. Or no, on the box. And then pointing up from the ramp.
Ooh.
No. Oh, on the ground.
Yes. Weight is always between ground and the small object. All right, so we got one there.
So why? On
Heck.
the box?
Why going that way on the box?
No.
This way. That's because it's going down, like, down. Like,
All right, so, okay, oh, sorry, my orientation was off. So the box is sliding that way.
yeah,
Okay, so what does that mean?
why? Arrow pointing the way.
Okay, there will be an arrow pointing that way, but acting on what object and what's the force?
The ramp.
Acting on the ramp? Is that, it's a matter of, I couldn't hear it, I wasn't trying to.
Yeah.
Okay, so there's force acting that way on the ramp? What force is it?
Why?
Friction.
Friction.
It is friction. Yeah, just like we had right there.
Oh.
So I have this friction acting down this way, so we'll call this F sub B. Where's the other, since they come in pairs, where's the other one?
Box.
Opposite.
Opposite on the box. Normal force is always gonna be perpendicular, not parallel. All right, two down, new voice. Said force on the ramp? What force? We have weight, normal, and friction. Those are the three we're dealing with right now. Acting which way on the ramp?
Downward.
So we have the weight of the ramp, and where's the other part of that force?
On the ground.
Acting?
Up.
All right, we're cruising here. All right, so we have only two small objects, again, small being not planet or moon size. And we have the two pairs of weight forces there, so weight is done. Let's start a new checklist there. Gravitational force taken care of. Because we're ignoring the tiny little gravitational forces, the ones that are on the order of 10 to the negative 40th newtons.
What are we missing?
Contact.
So, pardon?
No, that's fine.
We're missing contact forces.
We have a new voice here.
Normal force?
A new voice.
Okay.
Nothing wrong with your voice, Eddie, but I'm just saying, let's see if we can.
Wait, this is probably the box is sliding, right?
Yes.
Okay.
Well, actually, we don't know, there's not enough information, but, you can assume that's sliding.
So the one you drew is basically it's sliding on the right.
Yeah.
Okay.
But that's why earlier I said desired motion, it doesn't actually have to move for friction to be acting on it. It wants to move. Just like this box wants to move down the ramp, but friction's keeping it from doing it.
So normal force is Y?
Yes, normal force is Y.
So what if Y, the box go that way then?
The normal force on the box up and to the right? Yep, just like it was before. I guess.
And then the ramp Y will go down.
I assume down to the left. I didn't see your hand gesture, I was, that's right.
We still not done with number four?
Say it again?
We still not done with number four?
We're not done with normal force.
The ground and the ramp.
Yes. Apparently we've gotten away from the new voice here. The one time I put a student in tears once, surely I feel so bad about it still. I was doing one of these, had a complex problem up here, and I had students come up to the board to do it. And the student, I didn't realize, was so incredibly painfully shy. And so she waited till the end when the harder forces had to be done, and tears started streaming while she was standing at the board. That's one of the reasons why I don't do that anymore. However, I'm hoping from the safety of your seats, you might take chances. It's okay to take chances, make mistakes. And what's the third thing?
Get messy.
Thank you. Nothing to anyone else?